Welcome back. In this lecture, we will discuss mean and variance of probability distributions of random variables. Two technical terms: population, sample mean, sample variance, and normal distribution. Next, we are going to discuss two important characteristics associated with the probability mass function or probability density function. They are called mean and variance. For a random variable x, its statistical mean is denoted by expected value of x, and it is defined as sigma x fx, summation over x. Suppose fx is the probability mass function of a discrete type random variable, then we define its statistical mean or expected value as the product sum. That means each of the values taken by the random variable multiplied with the respective probabilities and adding together, and what we get a number, and that number is taken as the mean of the values of the random variable. It is not the ordinary mean, it is the weighted mean. That means every time we are multiplying the values with the corresponding weight. What is the weight? Here the weights are the respective probabilities. Okay. For our previous example case, the values of the random variables are 0, 1 and 2. This is the probability mass function defined by 1 by 4, this is 2 by 4 and this is 1 by 4. Then what is the expected value of that random variable? Expected value of counting number of heads or number of tails. Expected value is equal to, we are multiplying each of the values with the respective probability, that is 0 into 1 by 4. Plus 1 into f of 1. What is f of 1? 2 by 4 plus 2 into 1 by 4 and adding together, that is 0 plus 2 by 4 plus 2 by 4, that is 4 by 4. So the expected value is equal to 1. That means, what is the meaning that expected value of x is equal to 1? Here what is x? X is counting number of heads. Counting number of heads. So in the random experiment with a random variable counting number of heads, on the average we can expect 1 head. That is the meaning of expected value of x is equal to 1 for this situation. Okay. Here also it is clearly understood that the random variable taking the value 1 has the highest probability. It has the more weights as compared to the values 0 and 2. See, 0 and 2 has the weights or the probabilities as 1 by 4, but 1 has more weights as compared to the other 2. So it will be naturally the weighted average. It is also called a weighted average because we are adding this 0 into 1 by 4 plus 1 into 2 by 4 plus 2 into 1 by 4 divided by total weight. Here what is the sum of the weights? Sum of the weights is 1 by 4 plus 2 by 4 plus 1 by 4, that is 1. So it is called a weighted average. We can treat it as a weighted average. Now, for a continuous type random variable with the probability density function, we can define expected value of x as, instead of that summation, we are integrating every value fx with its densities, corresponding densities, integral x fx dx, and integrating from the theoretical possible values of the random variables, because a continuous random variable takes all some numbers, certain intervals, values lies in an interval in a number line. We can accommodate the entire number line by writing minus infinity to plus infinity. So we are integrating from theoretical lowest value to maximum value and multiplying together each of the values with the respective densities. Here each of the values with the respective probabilities, and that number is taken as the statistical average or the mean of the values taken by the random variable. Okay, here it is the mean of the values taken by the discrete random variable 0, 1 and 2. The next important characteristic is variance. So in order to define the variance of a random variable, we have to define expectation of x square, and by definition this expectation of x square is equal to sum of squares of the values multiplied with the respective probabilities and adding over x. And variance of x is defined as expectation of x minus e of x the whole square. On expansion we can have this as expectation of x square minus e of x the whole square. So if you are expanding this using the identity a minus b the whole square, we get x square minus 2x into e of x plus e of x the whole square. On simplification, we can see that this becomes expectation of x square minus e of x the whole square, because the expectation, statistical expectation, is linear in nature. That is, expectation of ax plus by is equal to a into expected value of x plus b into expected value of y. So using that formula, or by simplification, this variance computation formula reduces to expected value of x square minus e of x the whole square, where e of x square is given by summation over x square into fx. And similarly, for continuous random variable case, the variance for variance computation, the expected value of x square is given by e of x square is equal to what is the formula? Integral x square into the corresponding densities, integrating from minus infinity to plus infinity. And variance of x formula computation, variance of x is equal to also expectation of x square minus e of x the whole square. So these are the two important characteristics associated with every statistical distributions. So before defining the term sample mean and sample variance, we have to understand the definitions of population and a sample. Population and a sample. See here, population means statistical population. By definition, a statistical population is the collection of all data under study, or it is the collection of all characteristics under study. For example, if you are considering the marks obtained by students in an entrance examination, then the collection of all that marks is forms a statistical population. And if you are selecting the marks obtained by students in a particular center, that is called a sample. So we can define a population as statistical population as the collection of all characteristics under study, or the totality of all numerical values under study is called population, and a representative part of the population is called sample. And we are interested in measuring the sample mean and sample variance, because this sample mean can be treated as an estimate of the population mean, and similarly sample variance is an estimate of population variance. So there is a difference in ordinary computation of mean and variance of numerical data, and computation of sample mean and sample variance. Suppose we have n observations, x1, x2, etc., xn. Then we find the measure of central tendency. A measure of central tendency is the arithmetic mean, and another measure of central tendency is median, mean, median, mode, etc. These are the measures of central tendency. And measures of dispersion are standard deviation, or it's a square, that is called the variance. Square of the standard deviation is called the variance. Mean deviation, mean deviation about mean, mean deviation about median, etc. They are called measures of dispersion. So in the computation of measure of central tendency, we can denote this arithmetic mean by the symbol say x bar. Then this x bar is equal to sigma xi divided by total number of observation, where this I varies from 1 to n for raw data. And for a frequency distribution, if all these values, that means first value is repeating f1 times, second value repeating f2 times, etc., xn repeating fn times, then is called a frequency distribution. And for a frequency distribution, the mean computation formula becomes sigma xi fi divided by sigma fi, where the sigma fi is the total frequency. And in standard deviation computation or variance computation, by definition, variance, what is variance? Variance of certain set of data x1 is to etc. xn is defined as it is the arithmetic mean of squares of the deviations taken from the mean, that is sigma xi minus x bar the whole square, where I varies from 1 to n. The mean of squares of the deviations taken from the mean is called variance, and its a positive square root is called standard deviation. Standard deviation is equal to positive square root of variance. So these are the definitions we will apply in computation of a measure of central tendency and a measure of dispersion. But in statistical computation, we are interested in sample mean and sample variance, because they are estimates of the respective population mean and population variance. We have to consider independent observations. suppose this x1 is to etc. xn forms a sample of size n. Suppose this is a sample of size n taken from some population. Then sample mean x bar is equal to 1 by n into sigma xi, where I varies from 1 to n. And because here we have n observations, x1 is to etc. xn, all these observations are independent observations. So we can take the sample mean x bar is equal to 1 by n into sigma xi. That means we are using the same formula as in the case of computation of measure of central tendency. But in sample variance computation, we use the notation S square. Again we are taking sum of squares of the deviations taken from the mean, but we are dividing this with n minus 1. And here is the reason, because these deviations xi minus x bar, that is a property of arithmetic mean. If we take the sum of the deviations about mean, this total value becomes 0. That is a property of arithmetic mean. And corresponding to n observation x1 is to etc. xn, we can have n deviations, that is x1 minus x bar, x2 minus x bar, etc. xn minus x bar. But all the n deviations are not independent, because their total sum is equal to 0. Therefore, if we know the deviations, n minus 1 deviations, then the last one is the negative of the sum of the remaining deviations. So totally we have only n minus 1 independent observation. So in the sample variance computation, instead of dividing with the n, we are dividing this with the n minus 1. So that is a very important formula. Sample variance computation formula: S square is equal to 1 by n minus 1 into sigma xi minus x bar the whole square, where this I varies from 1 to n, and a sample mean, it was no change in the formula, same formula, because all the n observations are independent. x1 is to etc. xn are independent, so we are dividing with the n. For illustration of this concept, we can see the example. Suppose we are considering n values. For example, n values are 1, 2, 3, 4, 5. Then what is average of these 5 observations? 1, 2, 3, 4, 5. Average is 3. And if you are taking the deviations x minus x bar, so x bar is equal to 3 in this case. So x minus x bar means subtracting mean from every observation. Subtracting mean from every observation means 1 minus 3, that is minus 2. 2 minus 3 minus 1, 3 minus 3 0, 4 minus 3 1, and 5 minus 3, that is 2. Then what is the total sum? If you are adding this column, we can say that this total sum is equal to 0. And this property is true for every observations. So that is a property of arithmetic mean. An important distribution in the statistical analysis is normal distribution. A continuous random variable capital X is said to follow normal distribution with the parameters mu and sigma if its density function, probability density function, is given by the formula fx is equal to 1 by square root of 2 pi into sigma e raised to minus of x minus mu the whole square divided by 2 sigma square, where this x are the values of the random variable that can take any number in the number line, that is minus infinity, less than x, less than plus infinity. A random variable with this density function is said to follow normal distribution with the 2 parameters. Here what are the parameters? Parameters are mu and sigma. Here mu is the expected value of that normal random variable. So u of x is equal to mu, and variance of x is equal to sigma square, or standard deviation is equal to positive square root, that is sigma. And if we draw the graph of that normal distribution, we can see that a symmetry about the mean value, say mu. That means we can see that majority of the observations are clustering about the central value, that is the measure of central tendency. And this sigma square, or variance or standard deviation sigma, here the standard deviation equal to sigma, that will determine the shape of the normal curve. And as we know, the normal curve, so we can draw some normal curve. So this is the shape of a normal density function fx. We can see the shape is a bell-shaped curve, and it has a symmetry about the line x is equal to mu, because the majority observations are clustering about the central value, that is the mean value. So this mu determines the location parameter. Here what is mu? Mu is the location parameter, and sigma is the shape parameter. Because this, as the mu changes, the curve also changes, and the shape, the peakiness of this curve is determined by the parameter sigma. That means for larger value of sigma, the curve becomes peaker or flatter. If standard deviation is larger, the curve becomes flatter, and if it is smaller, the curve becomes peaker. So that sigma determines the shape of the normal curve, and mu determines the location of symmetry. So this mu and sigma are called location parameter and shape parameter. So, and for this normal curve, we can see a symmetry about the line x is equal to mu, and total area under this curve, that is, if we integrate this normal density from minus infinity to plus infinity, because this is the probability density function, we can see that total area under the curve is 1. And because of symmetry, to the right of x equal to mu, the total area is 0.5. To the left of x equal to mu, total area is again 0.5. Depends on the different values of this average, that means expected value or mean value. The normal curve is placed at different locations. Okay, and for different sigma, we can have different height of this bell-shaped normal curve. For mathematical study of that different normal curves, we can have a standardization, that is called the standard normal distribution. Standard normal distribution. That standardization is a new random variable that is given by a transformation x minus mu by sigma. If x follows normal distribution with the parameters mu and sigma, then the standardized normal random variable, this is called a standardized variable. And what is the transformation? Subtracting mean and scaling down by sigma. So this Z follows normal distribution with the parameters 0 and 1, and that is called the standard normal distribution. And for computation purpose or for all analysis purpose, we will depend on this standard normal density. And that standard normal density has the shape also bell shape, but it has the symmetry about the mean value. Here what is mean? Mean is equal to 0. So it is symmetric about the mean value, and the random variables are denoted by Z. So this is Z is equal to 0. So the standard normal distribution is always symmetric about Z equal to 0, and it has the standard deviation 1. So in the density function of standard normal distribution, fx, we can replace this mu by 0 and sigma by 1. For normal density, ordinary normal density, the density is given by fx equal to 1 by root 2 pi sigma e raised to minus of x minus mu the whole square by sigma square, where x varies from minus infinity to plus infinity. But in the standardized case, we can have another function. The density has another function, say phi z, and that phi z is obtained by replacing this sigma by 1, that is 1 by root 2 pi e raised to minus of, this is minus z square. This is e raised to minus of x minus mu the whole square by 2 sigma square. So this is minus z square by 2, where this z is also varying from minus infinity to plus infinity, that is minus infinity plus less than z less than plus infinity, and this will be the shape of a standard normal curve. And we can have different pre-computed areas. That means suppose this is our z equal to 0 and this is the ordinate, say z, then we can have the area up to, that means the probability that 0 less than z less than, say, some number ordinate, say z1, are pre-computed, and these probabilities are given in standard normal tables. So this area is given by integrating this function from 0 to the ordinate z1, this standard normal distribution phi z dz. All these pre-computed areas or definite integrals are given in standard normal table. Also we can have the symmetries. Total area to the right of 0 is 0.5 and to the left of 0 is also 0.5. Now see the different situations of probability evaluations using standard normal table. Probability that Z less than Z1. So this case depends on two different values of Z1, whether it is a positive number or a negative number. Suppose that Z1 is a positive number, then the standard normal density, see this is the shape of the standard normal curve. Suppose Z1 is positive, so we can place Z1 to the right of 0, and Z less than Z1 means all area, that means we are starting our integration from theoretical lowest value, that is minus infinity. So we are integrating from this minus infinity up to the point Z1. So that probability is given by minus infinity up to that 0 is 0.5 plus probability from that 0 to Z1. Probability from 0 to Z1 can be obtained from the standard normal table, that is probability that 0 less than Z less than Z1. Okay, and the second case, suppose this Z1 is a negative number, then what happens? If Z1 is negative, we can replace the Z1 to the left of 0, and Z less than Z1 is this tail probability. And how can you compute that tail probability? And we know that total area to the left of 0 is 0.5. So we are subtracting the area from minus infinity up to Z1. So this tail probability is obtained by subtracting from 0.5 the area up to Z1. Because of symmetry, this is equivalent to 0. Probability that 0 less than, suppose this is a negative number, say Z1 minus Z1, then probability that 0 less than Z, say less than Z1. Because of symmetry, that means suppose we have the probability computation from minus 2 to plus 2. Suppose this is a required probability, then because of symmetry, from the standard normal curve we can compute the probability from 0 to 2. That probability will be same as probability from minus 2 to 0. So if this minus Z1 is a negative number, then we can subtract from 0.5 the probability up to the corresponding positive value. Suppose Z is greater than Z1, where this Z1 is a positive number. Z greater than Z1 means this is the tail probability, and that tail probability is also obtained by subtracting from, that is probability that Z greater than Z1 is equal to 0.5 minus probability up to Z1, that is probability that 0 less than Z less than Z1. That is also a pre-computed area. We can obtain that from the standard normal table. And if it is a negative number, suppose this is a negative number, say minus Z1, then the total probability Z greater than that negative number. So this is the major area. So this computed area is given by, if it is a negative number, that is probability that Z greater than that minus Z1 is equal to the right of 0, the total area is 0.5. So we are adding that 0.5 with the probability up to the corresponding positive value Z1. That is 0.5 plus probability that 0 less than Z less than the positive number, say Z1. Because of symmetry, the area from minus Z1 to 0 is same as area from 0 to Z1. We are adding. So that area or this tail probability must exceed 0.5. And the final case, that is probability computation of Z1 less than Z less than Z2. Suppose both Z1 and Z2 are positive numbers. So suppose this is Z1 and this is Z2. So this is the required area. And how can we measure that area? Using standard normal table, we can measure this area as, first we can compute the total area from 0 up to Z2. From that area, subtract the area from 0 to Z1. So this is equivalent to, so this probability is equivalent to probability that 0 less than Z less than Z2, because Z2 is the larger number, minus probability that 0 less than Z less than Z1. Whenever this Z1 and Z2 are positive. If the sign changes, then we can do as in the previous case. So this normal distribution is an important distribution we are going to use in our upcoming modules, in particular for studying statistical inference and testing of hypothesis, etc. Okay, thank you.